In an equation, you can compare moles to moles. Let's practice. 1 mole of nitrogen will combine with 3 moles of hydrogen to produce ammonia. Here's my mole-to-mole ratio. For every 1 mole of nitrogen, I have 3 moles of hydrogen. I can also write that ratio in a reciprocal form. I can write 3 moles of hydrogen for every 1 mole of nitrogen. I can write mole-to-mole ratios for anything in a chemical equation. Let's try another one. 2 moles of ammonia for every 3 moles of hydrogen. Here's another example. Let's write a few mole-to-mole ratios. 13 moles of oxygen for every 8 moles of carbon dioxide. Or I can switch those because the ratio is the same. Mole-to-mole ratios come in very handy with stoichiometry problems. Here's an example. How many moles of H2O will be produced by 4.8 moles of O2? Where do I even start with this problem? Well, I would suggest starting with what they give you. They give you moles of O2. So let's start there. 4.8 moles of O2. Okay, let's draw a line and put it over a 1. Now I need to do a mole-to-mole ratio. I know that it's talking about oxygen and it's asking me about water. So let's do a mole-to-mole ratio there. I know that for every 13 moles of O2, I have 10 moles of H2O. My units will cancel, leaving me with moles of H2O, and that's what the problem asks for. So I multiply that out and I get 3.69 moles of H2O. Let's round up for significant figures. And there's my answer. Here's another example. If there are 5.6 moles of oxygen, how many moles of carbon dioxide can be produced? And they give you the equation. Now here's a hint. Always make sure the equation is balanced. In this case, the equation is not balanced, but you can balance it with the tally system. Once you tally either side to make sure that they are equal, you should get the final equation. Here's the balanced equation. Now that we have the balanced equation, let's answer the question. I start with what they give me, 5.6 moles of oxygen. I then need to find my mole-to-mole ratio. I'm going from oxygen to carbon dioxide. So I look at my balanced equation and I want the coefficient here in front of oxygen, and I want to compare that to the coefficient here in front of carbon dioxide. Let's write my mole-to-mole ratio. Here's my mole-to-mole ratio. For every 5 moles of oxygen, I have 4 moles of carbon dioxide. Notice that I'm abbreviating moles with just MOL. My units will cancel. Moles of oxygen on the denominator cancels with moles of oxygen on the numerator. Then I take it to my calculator and I multiply. I get 4.48 moles of carbon dioxide. For significant figures, I'm going to round. Here is my final answer. Here's a little hint for section 6.3. We know how to compare moles to moles, but you'll be using masses in experiments. So we need to be able to compare masses to moles because equations only do mole to mole ratios. They are not mass to mass ratios. Do you remember the mole map? Here is the lovely mole map. If we measure masses, we can mathematically find the amount of moles, because if we're given masses here, we can use the periodic table to convert to moles. If we have moles, we know we can do a mole-to-mole ratio in any balanced chemical equation. Remember, chemical equations do not compare masses to masses. They compare moles to moles. Here's an example problem. How many moles of carbon dioxide form when 25 grams of methane reacts with excess oxygen? I'm just going to show you how to set up a problem like this, and you'll come across these in 6.3. So I begin with what they give me. They give me 25 grams of methane, so that's what I'll write. So I have 25 grams of methane. Now I know I need to go from grams to moles of methane, and I use my periodic table to do that. I know that I have 16.042 grams of methane in 1 mole of methane. I get this number by going to the periodic table and adding up 4 hydrogen plus 1 carbon. Now if I stop here, I know how many moles of methane I have, but that's not what the problem asks. The problem asks me to find the moles of carbon dioxide. So I need to go a little bit further. I know that I need to do a mole-to-mole ratio, and I can do that because my equation is balanced. So I know I have 1 mole of methane for every 1 mole of carbon dioxide. Let's make sure I end up with the right unit. I end up with moles of carbon dioxide, and that's what the problem asks. Do all of the units cancel? Yes. All of the units cancel. Moles of methane, grams of methane, grams of methane. Okay, so now I take my calculator and I would finish the problem here and I would get moles of carbon dioxide. Well, there's a hint for 6.3, but in 6.2 we learn the importance of mole-to-mole ratios, that a balanced equation gives us mole-to-mole ratios.